In this video, we're going to begin section 10.4, talking about polar coordinates and coordinate conversion. Up to this point, we've learned graphs on the rectangular coordinate system. We know how to plot points, graph lines, and most recently, even parametric equations. Now we want to look at a different coordinate system called the polar coordinate system. So it's still going to appear like the rectangular coordinate system, but now we are graphing r comma theta as an ordered pair. And r is really just the radius of a circle, or the directed distance from a fixed point called the pole or origin, which is of course that point right in the middle. And theta is the directed angle from an initial ray called the polar axis, which is this guy. And so basically it's just the angle from the positive x-axis. That's what r theta is. So we're going to do some practice with graphing, but typically what's going to happen is you're going to draw concentric circles. Try to make them better than mine. Try to make them equally spaced apart. Whereas the first circle has a radius of 1, the second circle has a radius of 2, the third circle has a radius of 3, etc. So if I wanted to plot the point, say 2 comma pi over 2, well, then I'd have to remember that this would be 0, this would be pi, making this pi over 2, making this 3 pi over 2, and sometimes you'll see these drawn out already with some extra lines, which of course this would be pi over 6 and pi over 3 and so on, and I'm not going to draw all those in, but of course you could if you needed to. So for instance, just for our first example, to graph 2 comma pi over 2, I would go 2 and then go pi over 2 from here. So really I'm looking at a ray that goes to 2 and that is pi over 2 from the polar axis, or the positive x-axis. So let's just do a couple of practice, and notice for each of these I've given you only positive values. So we'll take a look at negative values in just a moment. But for the first one, 2 comma 2 pi over 3. Remember, 2 tells me to go out 2 places, and then I'm just going to move to 2 pi over 3. And so that means I'm looking right here, because this measurement is 2 pi over 3. So my solution is a ray that ends at 2 pi over 3. Again, at the radius of 2. For my second one, I have 1 comma 11 pi over 6. So I go 1, and then 11 pi over 6 is all the way to here. So again, that's going to look just like this, without the circle. For the next one, 3 comma pi over 3. So I'm going out 3, and then pi over 3 is right here. So that's going to be this line, 3 comma pi over 3. And for the last one, I have 3 comma 7 pi over 3. So 3 is here, and then if I go all the way around, this is 5 pi over 3, this is 6 pi over 3, this is 7 pi over 3. So this is the exact same. Now, the reason I gave you two that were the exact same is because I wanted you to understand that while on the rectangular system, every point or every coordinate on the rectangular system is unique. So if I say 4 comma 5, that's one position, and that's the only way that I could label that point. Whereas on the polar coordinate system, these two are actually the same point. And so it's okay for us, whenever we have an r comma theta, an equivalent an equivalent polar coordinate would be r comma theta plus 2 pi. So if I add 2 pi, which is what I did here, I just didn't tell you that's what I was doing. 2 pi is 6 pi over 3. I added that to pi over 3. to get 7 pi over 3. So I used this without telling you just to show you that those things would be the same. So this is one of the things that you'll need to understand about rectangular coordinates, is that we can always add 2 pi, keeping the same radius, and have the exact same point. Let's look at just a few more graphs now. This is our first negative value, and I also wanted to give some of these to you in degrees as well. Typically we'll deal with radians, but sometimes you might see them in degrees. So of course this would be 0 degrees, and this would be 90 degrees, and this would be 180 degrees, and so on. So for my first example, I'm looking for -2, 45, and 45 degrees would just be right here in the middle of these two. But this is our first negative. So when you're graphing -2, 45, what you want to do is look at where 2, 45 degrees is first. And that would be 2 units out and 45 degrees. So this would be 2, 45. So -2, 45 would just be in the opposite direction. So that is the correct answer for -2, 45. Now let's take a look at 2, 225. Well, 225 is 180 plus 45. So 2, 225 would be from here. This would be 180 plus another 45, and yes, that's the exact same place. So we talked on our last examples about the fact that I could have r theta represented as the same point as r, theta plus 2 pi. Another way to do this is to say if you have r theta, that's the same as -r, and then theta plus pi. So for instance, -2, 45 is equivalent, using this second expression, to +2, 45 plus pi, or pi is obviously equal to 180, so 2, 225. So that's where that second value came from. So let's take a look now at my second example, and notice they're all 4 very similar. So I bet you can see where I'm going to go with this. We're back to radians now. -3, 2 pi over 3. Remember, the way that we did this before is we looked at where +3, 2 pi over 3 would be, which would be right here. And instead we just went in the opposite direction. So this is -3, 2 pi over 3. And another way you can think of that is, instead of going +3, is to actually go -3, and then this would be 2 pi over 3 from there. So that's this point. -3, -4 pi over 3. So now we're getting really crazy here. We've got a negative and a negative. So -3 over here, -4 pi over 3 says instead of going counterclockwise, go clockwise. So this would be 3 pi over 3, and I need another third pi, and yes, I've ended up exactly where I was again. And again, how did I do that? I really just used this one, except instead of adding 2 pi, I subtracted 2 pi, which is okay too. So that's both of these now in the same position. Now let's take a look at 3, 5 pi over 3. Well, we hopefully can already see that if I use, oops, that was the wrong one. If I use this guy says I can change this to negative. So now that's -3, instead of 5 pi over 3, I can add pi, or I can take away pi, so this could really be plus or minus. So if I take pi away from that, that's 2 pi over 3, which is exactly what I had graphed the first time. So again, let's just verify that that is the same position. 3, 5 pi over 3 would be right there. Okay, and then for the last one, 3, negative pi over 3, again 3, and then I would go now in the negative direction, negative pi over 3. And again, the reason that I bring that up is, again, because you might be asked to find many more representations of the exact same point And all I did was used variations of these two identities. So keep those in mind as we're going forward through this lesson. The other thing we want to be able to do is to convert between rectangular and polar coordinates, so from one to the other. So what I want to do is I want to think about what our normal rectangular coordinate system would look like, and I would have some point that I would label with x, comma, y. This would be the x-axis, this would be the y-axis. Now, if I overlaid the polar coordinate system right on top of this, then this point would now be considered r, comma, theta instead of x, comma, y. And I would have this line that I would draw in, and this would be the measure of theta, and this would be the measure of r. So going back to what I had for xy, this distance would be x and this distance would be y. And this would make a nice right triangle. So let's take a look at how I might relate the two systems to one another since they overlap each other so well. So first of all, the fact that this is a right triangle, so these are just going to be all the relationships. And then we'll talk about how we might use those to go from one to the other. So one relationship is that x squared plus y squared is equal to r squared, because that's the Pythagorean theorem. Now that's the only one that I can use with the Pythagorean theorem, but because I have a right triangle, I can also use sine, cosine, or tangent. So I can use that sine of theta is equal to y over r. I can say that cosine of theta, because sine is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. Now, to go from rectangular to polar, or to go from polar to rectangular, we have to look at which ones make the most sense for which ones. Keeping in mind, if I have, oh, this was supposed to be r. I'm sorry, you guys should have just reminded me that was r. If I have an x and a y, then I'm going to use that to go from rectangular to polar. So as I can see, here is where I have both the x and the y. And why did I say that? Because I'm going to be given x and y, because I'm going to start with xy, and I need to convert to r theta. So it makes sense that I'm going to choose the two that involve xy. So from rectangular to polar, I'm going to use x squared plus y squared is equal to r squared, and that tangent of theta is equal to y over x. From polar to rectangular, I'm going to have r theta, I'm going to need to convert to xy. So that's why I'm going to use cosine and sine. So I'm going to use sine, and I'm not going to actually write it like that because I'm going to actually multiply by r on each side. So I'm going to write that y is equal to r sine theta. And same thing here, multiplying by r. I'm going to say x is equal to r cosine theta. So let's use those now to come up with our solutions for our conversions back and forth. Let's look at our first example. I'm asking you to plot the polar coordinate, then find the corresponding rectangular coordinate for that point. So again, if I had a coordinate plane, I would just draw a couple of circles, and I just need two. And if I'm plotting the point, that was a bad second circle. If I'm plotting the point -2, 11 pi over 6, it's easiest to plot the point +2, 11 pi over 6, which is right here, and then reflect that across the origin. So this is the point -2, 11 pi over 6. So that's the first part, is just to plot the point. Now what I have to do is I have to write the rectangular coordinate. So this is obviously given to me in r theta. And I need to turn that into x, y. Now we just talked about how to do that. We said, okay, we can write x is equal to r cosine theta, and y is equal to r sine of theta. So really, I'm taking r, which is -2, and then cosine of 11 pi over 6, oops, I keep doing that, 11 pi over 6, and sine of 11 pi over 6. Now, of course, there's different ways to find cosine and sine of 11 pi over 6, but the easiest is the unit circle. And typically, you should have, hopefully, memorized just the first quadrant of the unit circle, because if you have, then this is actually very, very easy. If we're looking at 11 pi over 6, which we know is just down here, if we're looking at that, all we're going to do is compare it to pi over 6 and then take a look at the signs. How would the signs be different in that fourth quadrant? So if I'm looking at pi over 6, remember that the first value is cosine and the second value is sine. So this is sine or cosine of pi over 6, and this is sine of pi over 6. Now, why is that important? Because I'm looking for 11 pi over 6. So what does that have in common? Well, this point, a radical 3 divided by 2, comma 1/2, down here would be radical 3 over 2, comma -1/2. Why? Because it's in the fourth quadrant. So the first value, the x value, is positive and the y value is negative. So again, that's how it helps me, because now I have -2 times the cosine of 11 pi over 6 is radical 3 over 2. That gives me negative radical 3. And the sine of 11 pi over 6 is -1/2, which gives me positive 1. So my new value, my new rectangular coordinate, is negative radical 3, comma 1. And so if I were drawn to scale over here, it would make sense that this first value would be negative because it's here on the left-hand side of the origin, and the second value would be positive of 1. And so hopefully it should make sense if I overlaid those two graphs. Now let's look at an example in reverse. We are given a rectangular coordinate and we want to plot the point and then find two sets of polar coordinates. So I'm going to start just by plotting the rectangular coordinate. And obviously I'm going to be over here in the second quadrant, 4, 5, 6, 7, 8, 9, and that point is -5, and then this is about 8.7. So that's about where this point is. So this is the point -5, comma 5 radical 3. So that's the first part. Obviously that's the super easy part. From here I want to find a set of polar coordinates, and then we'll worry about the second set in a little bit. So for the first set of polar coordinates, remember I'm using two facts. I'm using the fact that x squared plus y squared is equal to r squared. And then for the sake of solving, of course, I'm just going to think about that as the square root of x squared plus y squared is equal to r. So let's do that one first. If x is -5 and y is 5 radical 3, I'm going to square both of those and find the sum, then take the square root. So -5 squared is positive 25. 5 radical 3 squared is 5 squared times radical 3 squared, which is 25 times, remember the square root and squared cancel each other out, so it's 25 times 3, or 75. Which of course means I have the square root of 100, which means, oops, 10 is r. r is 10. So in my new ordered pair, r theta, r is 10. So now I have to find theta, which is just a little bit harder. So here's what I'm going to do. I'm going to use the fact that tangent of theta is equal to y over x. And that means that theta is equal to the inverse tangent of y over x. So if I take the inverse tangent of each side, it gets rid of tangent from the left. So using that fact, we're going to find a reference angle, and then we'll take a look at the position of the rectangular coordinate to find the correct angle, theta. And hopefully it will make sense as I go through it, and if you haven't heard that term reference angle before. So theta is going to be equal to inverse tangent of y over x. Y is 5 radical 3, x is negative 5, but when we do this, we don't deal with the negatives. Just look at the 5, because we'll deal with the negative in just a little bit. So really I'm looking at the inverse tangent of radical 3. And so what I'm looking for is where, and of course you can break out your calculator. It's just a little bit more complicated because you have to make sure if it's in radians or degrees, and then if it gives you the answer in radians, does that answer make sense to you? So let's just look at the unit circle, and I'll let you figure out the calculator part by yourself. If I need y over x to be equal to radical 3, then clearly I'm not looking at pi over 4, because if I took y divided by x, I would get 1. So it's not that one. So let's look at pi over 6. If I took y over x, that would be 1/2 divided by radical 3 over 2, which would give me 1 over radical 3, which is not what I want. So my best guess is it's going to be pi over 3. Let's do y over x, radical 3 over 2, divided by 1 over 2. That would give me radical 3 over 1. So my reference angle is pi over 3. Now that does not mean theta is pi over 3. That means my reference angle of theta is pi over 3. So here's how we determine this. Let's look at where our rectangular value is located. That's telling me that this is pi over 3. So obviously this is x, and this is y, and this is r. This guy is pi over 3. So how do I know, because that's not what I want, remember I want this guy, well all I have to do in that situation is take pi minus pi over 3, which would of course be 2 pi over 3, and that is my correct angle. So 10, 2 pi over 3 is my solution. Now, if I needed to find another set of polar coordinates, remember the sky is the limit. We talked about I could make r negative, which would be negative 10, and then add or subtract pi. So if I added pi to that, that would be 5 pi over 3, and that is another set. I could use any of those strategies that we talked about before by either negating pi, adding 2 pi, subtracting 2 pi, etc. Hopefully that was a good basis for which to start to build our foundation of polar coordinates and polar graphs. So coming up next, we're going to look at polar graphs.